In this video, we're going to begin talking about polynomial functions, including what exactly a polynomial function is, and learn a little bit about how to graph these types of functions. So let's start with our definition right away. We are going to let n be a non-negative integer. So that's non-negative whole numbers. And we're going to let an minus 1, an minus 2, all the way through a0 be real numbers. So they can be positive, negative, decimals, whole numbers, fractions, all sorts of stuff. Then a function that looks like an times x to the n plus an minus 1 times x to the n minus 1 all the way through a1 times x and a0 is called a polynomial function of degree n. All right, so a polynomial is basically just adding together a bunch of powers of x. The powers on x have to be whole number powers, so you can't have roots for your powers. And we have to have non-negative powers, so there's nothing in the denominator involving x. Those are polynomials. And the domain of a polynomial function is all real numbers. And the graph of a polynomial function is always continuous and smooth. Our domain, negative infinity to positive infinity, and the graph is continuous and smooth. So the graph being continuous just means that you can graph it without lifting your pencil off the paper. There's going to be no holes or breaks or jumps. The graph being smooth just means you don't have any really sharp corners. It's just nice and goes up and down, but doesn't have sharp corners or edges. First thing we're going to learn about our polynomial functions is the leading term test, which tells us the end behavior of the function. So the leading term test says as x approaches infinity or x approaches negative infinity, so as x gets really, really big or really, really small, a polynomial f of x eventually becomes forever increasing or forever decreasing. And it follows the general behavior of the very first term, an times x to the n. So what this is saying is when you plug in really, really big numbers, whether they're really, really big positive or really, really big negative numbers, it's that leading term that actually controls the behavior of the graph on the ends. So you only have to see what happens to that first term, and that will tell you if the graph is going up forever or down forever when you go out to the sides. Let's do an example where we figure out the end behavior of the graph. determine the end behavior of the graphs of, first one's going to be f of x equals negative 0.3 x to the fourth minus 5x squared minus 3x plus 4. So if we're trying to figure out what this graph looks like at the ends, so for really, really big values of x in either the positive or negative direction, we only have to look at what happens to this first term. Because when you plug in really, really big values, that x to the fourth dominates the rest of the equation. It ends up being so much larger than everything else that the rest of that doesn't really matter as much anymore. So let's first figure out what happens as our x gets really, really big in the positive direction. So as x goes to infinity, this first term, negative 0.3 x to the fourth, what happens to that? So think about plugging in really, really big numbers into that x to the fourth. It's going to be even bigger. So it's going to be some really huge number times a negative 0.3. Well, it's still going to be a huge number, but that negative makes the whole thing go to the negative side. So it's going to go to negative infinity. So this means that the entire function also goes to negative infinity. It follows the behavior of that first term. All that this means is that the graph is going down on the right side. I know it's the right side because I had x going to all of our positive numbers. So the graph is going down on the right side. And now we just have to see what happens on the left side of the graph. So for the left side, we have to look at what happens as x goes to negative infinity. You still look at that first term. And what happens to this? When I plug in really, really huge negative numbers and raise it to a fourth power, they're still going to be really, really huge, but a negative to the fourth power is positive. And then I have positive huge number times a negative number. That makes it go to a negative huge number. So our function is going to go to negative infinity, just like that first term does. This means our graph is going down on the left side as well. So looking at the first term, your leading term test here, it tells you what happens on the ends of the graph, but it tells you nothing about what happens in the middle. So right now, I really don't know what this function looks like if I graph it. All that this leading term test tells me is that over on the left side and over on the right side, my graph is going down forever. So it's going to be going down over here and down over here and in the middle. We don't know that yet, but we know at least it's going down on both sides. We're going to learn more about what happens in the middle during this video. All right, let's do another example, our part B. We're going to do the same thing with a different function. We have g of x equals 6 over 7 times x minus 9 to the fourth times x plus 4 squared times 3x minus 5. Now, we know to determine the end behavior of the graph, we need to use the leading term test. I don't know my leading term right now, though, because my function is completely factored. It's not distributed completely out. Don't worry, though. We don't have to completely distribute everything to figure out the leading term. To figure out the leading term, we can just imagine that we're distributing everything. I know I would have that 6/7 multiplied on it. If I multiply out this x minus 9 to the fourth, I know that the highest power of x I'm going to get is an x to the 4th. If I multiply out x plus 4 squared, my highest power of x is going to be x squared. And in my last factor here, my highest power of x is 3x. So if I multiply all of that together, I get my leading term, which is 18 over 7 times x to the 7th. The rest of this polynomial, I don't know what it is. We'd have to distribute everything, but we also don't care what it is at this point. We just want to find out the end behavior, so we only need that first term. So now let's check what happens as x approaches infinity. So as we go to the right side of our graph. As we go to the right side of the graph, our leading term, what happens to that? Really big positive numbers to the 7th power are going to be really big positive numbers. Multiply it by another positive number and it stays positive. So we're going to positive infinity. This means that our whole entire function is also going to positive infinity. And our end behavior is that our graph is going up on the right side. Now we just have to determine what happens on the left side of the graph. So on the left side, we have to look at what happens as x approaches negative infinity. When we approach negative infinity, what happens to this 18 over 7 x to the 7th? Well, a negative huge number to the 7th power is going to be a negative huge power still. Negatives to an odd power are still negative. And then I'm multiplying it by a positive number, which keeps the whole thing negative. So this is going to negative infinity. That means my entire function is approaching negative infinity. And that means the graph is going down on the left side. So what does this graph look like? Well, we don't really know anything about it other than what happens on the ends. All that we know right now is that if I were to graph the function, we have no idea what happens in the middle, but we know we're going down on the left. We have no idea what happens in between, but we end up going up on the right. So there's a bunch of stuff in the middle. It could be going up and down like crazy, but we know at least what happens on the ends. Great. Now we need to learn about the zeros of our polynomials. So a definition. The values of x for which a polynomial f of x equals 0 are called the zeros of the function. So the zeros of our function are actually the solutions to the equation f of x equals 0. That means they're the roots of the equation, and it also means that they are the x-intercepts of our graph. So anytime you see roots or zeros or x-intercepts in reference to a polynomial, they're all talking about the same exact thing. Let's do an example where we find all of the zeros of a polynomial. Find the zeros of the function f of x equals 4x to the 3rd minus 4x squared minus 25x plus 25. So what I need to do to find my zeros is I need to solve the equation 4x to the third minus 4x squared minus 25x plus 25 equals 0. And my solutions to that will be the zeros of this polynomial. So how do we solve this? Well, I personally would factor it, and I would factor by grouping. So I'm going to look at just these two guys first, and then look at the next two guys. When I look at my first two terms, I'm going to figure out what the greatest common factor is and factor it out. I see they both have a 4 in common, and they also both have at least an x squared. So if I factor out 4x squared, I have an x and a minus 1 left behind. Now I look at the next two. What do they have in common? Just the 25. I'm going to pull out the negative 25 just because I have the negative in the front there. And when I pull out negative 25, I get x minus 1 in the parentheses. Now let me look at these two terms. I have 4x squared times x minus 1, and I have 25 times x minus 1. What they have in common is an x minus 1. So I'm going to factor out that x minus 1. And that leaves a 4x squared and a minus 25. And now I have just a product equaling 0. So we can use our zero product property from one of our previous videos. This tells me either x minus 1 is 0 or 4x squared minus 25 is 0. Solving the x minus 1 equals 0 just involves adding 1 to the other side of the equation. So I get x equals 1. That's one of my zeros. And to solve this equation, I'm going to add 25 to the other side. Divide by 4. And then take a square root using my square root property. So I get plus or minus the square root of 25 over 4, which simplifies to plus or minus 5 over 2. So this particular polynomial function had 3 zeros. X equals 1, x equals positive 5 over 2, and x equals negative 5 over 2. Now, it is possible for a polynomial to have a 0 happen more than one time. So if that happens, if a polynomial has a factor of x minus c appearing k times, then c is a 0 of multiplicity k. So by a factor appearing k times, we just mean that if this polynomial is completely factored, you're going to have an x minus c to the k power in that fully factored form. Now, depending on the multiplicity, the graph does different things. If the multiplicity is odd, the graph will cross the x-axis at that 0. So whenever that multiplicity is an odd number, the graph crosses the x-axis at that point. This is called a cross point. And if the multiplicity is even, the graph touches the x-axis at C, and then it turns around. And this would be a touch point. So if the multiplicity is odd, the graph of the function is going to touch x equals C and go through that x-axis at that point. But if the multiplicity is even, it's going to touch the x-axis, x equals C, but then immediately turn around and go the other direction and not actually cross at that point. Let's do an example where we find the zeros and multiplicities for some various polynomials. So determine the zeros and multiplicities for the following polynomials. Our first one is p of x equals -3/5 times x plus 3 to the 4th times 5x minus 1 to the 5th. Now this one's actually kind of nice because it's already factored for us. When I'm trying to find the zeros, it helps to have it completely factored. So remember, your zeros are when the entire polynomial equals 0. This -3/5 will never be 0, but this tells me that either x plus 3 to the 4th is 0, or 5x minus 1 to the 5th is 0. So for this one, this guy is going to equal 0 when x is equal to -3. And we can get the multiplicity of that 0 by looking at the exponent. This is multiplicity of 4. For this guy, this is going to equal 0 when x is 1/5. Just imagine solving that equation. And the multiplicity of this 0 is given by that exponent, so it's 5. Now what does this mean? It means if you were to graph this function, at x equals -3, the graph would touch it and then bounce and go the other direction right after touching. And at x equals 1/5, the graph would pass through the x-axis at that point. We're not going to graph this one thoroughly, but I did prepare the graph for you so you can see that that's what happens. If you were to graph this function, it's going to look something like this. This is a very, very rough sketch. Up here, this is 100,000, just to get you an idea. It's a really strange looking graph. It goes up really high, but here I'm counting by ones. So the graph of this function very, very roughly looks like this. Goes down and bounces. Goes up. And then it crosses there. Something similar to that. That's a very, very rough sketch, but it does end up bouncing here at -3. That means that we had an even multiplicity for our 0. It touches the x-axis and turns around. And over here at about x equals 1/5, it touches the x-axis and goes all the way through. That one's a cross point. Let's do another one that's not going to be fully factored for us to begin with. So find all the zeros in the multiplicities for q of x equals 2x to the 6th minus 14x to the 4th. To find the zeros, we know we need to solve our function equals 0. And we should do this with some factoring. Pull out the greatest common factor. They have a 2 and an x to the 4th in common, leaving an x squared and a minus 7. So the 2 isn't going to be 0, but I have x to the 4th equals 0, or x squared minus 7 equals 0. This guy, I take a 4th root and I get x equals 0, and the multiplicity is going to be 4 because that was the exponent on that value. Now for this guy, I would get x squared equals 7, which means x is plus or minus the square root of 7. The multiplicity of each of those is just 1. You might think it's 2 because I had an x squared, but notice that is supposed to stand for 2 different x values, and I got 2 different x values in my solution. So each one just has multiplicity 1. And what this means is that at 0, the graph is going to touch the x-axis and bounce off. And at positive and negative root 7, the graph is going to cross the x-axis. Again, we're not going to graph this one quite yet, but I am going to show you a very rough sketch that shows exactly what we just observed. So here is our positive root 7. Here's our negative root 7. And the graph of this function looks something like this. It goes down and crosses at negative root 7. It comes up, touches at 0 and bounces off, goes down again, turns around, and goes through at positive root 7. It's similar to that graph. Not exactly, that's a very rough sketch, but I just wanted to emphasize the crossing and the touching that we get from our multiplicity. All right, now we need to learn about a very, very powerful theorem called the intermediate value theorem. The intermediate value theorem says, let f of x be a polynomial then for a less than b, if f of a and f of b have opposite sign, then f has at least one 0 on the interval a to b. So by opposite signs, this just means one of them is positive and one of them is negative. If that happens, then at least once in between those two numbers, you have a 0. Now, this theorem does not tell us what the 0 is. It just tells you, okay, between these two numbers, there is a 0. So let's do an example where we use this theorem. So show that the function f of x equals x to the 4th plus 6x to the 3rd minus 26x plus 15 has a 0 on the interval -4 to -3. I'm going to show this by using my intermediate value theorem. So what I'm going to do is I'm going to evaluate what f of -4 is and what f of -3 is, and hope they have opposite signs. So f of -4, well, that's -4 to the 4 plus 6 times -4 cubed minus 26 times -4 plus 15. This equals 256 minus 384 plus 104 plus 15. And when you add all of those together, you get -9. Now let's see what happens at -3. F of -3 is -3 to the 4 plus 6 times -3 cubed minus 26 times -3 plus 15. This is equal to positive 81 minus 162 plus 78 plus 15. And when you add those all up, you get 12. So I know f of -4 is a negative number, and f of -3 is a positive number. They have opposite signs, so this means that by the intermediate value theorem, we have a 0. So the intermediate value theorem says we have a 0 on that interval. We have no idea what the 0 is. We just know there's some number between -4 and -3 that will give me an answer of 0. Now, the intuition behind this intermediate value theorem is actually pretty easy to see when you think about the graph. So we know nothing about the graph of that function other than what we just found. Way up at the top. And 1, 2, 3, 4, 5, 6, 7, 8, 9. We had f of -4 equals -9. F of -3 equals positive 12. And what do we know about polynomials? We know they're continuous and they are smooth. So if I were graphing this polynomial somewhere between -4 and -3, I would have to cross the x-axis because that's the only way to get from that point up to that point. We have to cross the x-axis at some point in between because my graph is supposed to be continuous and smooth. So whatever value that is where we cross, that is going to be our 0. All right. So now we need to learn how to graph some polynomials. I'm going to give us a guide for how to graph a polynomial, and then we'll do a couple graphing problems to finish up this video. One thing we should point out before we graph is that if f of x is a polynomial of degree n, meaning the highest exponent is n, then it has at most n minus 1 turning points. So a turning point is just where the graph changes direction. It changes from increasing to decreasing or decreasing to increasing. So if you have a degree n polynomial, it can change direction up to n minus 1 times, not any more than that. Now our technique for graphing. And this technique here is going to give you a sketch of the function. It's not going to be a completely precise graph, but it's going to be very close. The first thing we should do when we're graphing, determine your end behavior. So that's what we did at the beginning of this video, figuring out if the graph is going up or down on both the left and right sides by using our leading term test. Step 2, find your y-intercept and the zeros with multiplicities. We find the y-intercept the way we always do, plugging in x equals 0. To find all the zeros in the multiplicities, we do what we did earlier in this video. So then you would be able to plot those points on the graph. You know the end behavior, and you know if the graph is going to touch your zeros or if it's going to pass through the zeros. Step 3 is find several points between consecutive x-intercepts. And then connect. So that step 3 is just to help your graph be a little bit more accurate. You can figure out the general shape without doing that step 3, but step 3 will help you figure out how high the graph goes and how low the graph goes in between all of our x-intercepts. But it's still not going to be 100% precise. We're going to learn some techniques in calculus that help you graph much more precisely, but we're not quite there yet, so you'll have to wait for when you're in your calculus class. So let's use this technique to graph. Let's graph g of x equals negative x to the third plus 4x. And let's start with the end behavior. What happens as x approaches infinity? Well, remember, as x approaches infinity, we have to look at what happens to the leading term of our polynomial. So I have to see what happens to negative x to the third. As x goes to infinity, our negative x to the third, what happens to that? The x to the third would go to positive infinity, but then I have a negative in the front, so it goes to negative infinity. When instead I have my x approaching negative infinity, what happens to negative x to the third? Well, a negative huge number to the third power would be a negative huge number, but then this extra negative makes it positive. So my end behavior is it's going down on the right side and up on the left side. So that gives me the very ends of the graph. Now let's figure out what happens for our y-intercept and our zeros. So our y-intercept, we get that by calculating what happens when our x is equal to 0. So g of 0 would be negative 0 to the third plus 4 times 0, which is 0. So my y-intercept is the point 0, 0. Now for my zeros, we have to solve negative x to the third plus 4x equals 0. And I'm going to solve this by factoring. I'm going to pull out a negative x, which leaves an x squared minus 4. And I can actually factor that further because I have a difference of 2 squares. So this is negative x times x minus 2 and x plus 2. Looking at each of these factors, I can pick out my zeros. This first one is 0 when x equals 0. My second factor is 0 when x minus 2 equals 0, which means x equals 2. And my last one is 0 when x plus 2 equals 0, which is when x is negative 2. And all of these have multiplicity 1 because I don't have any exponents on those factors. So let me write down what we have so far in our graph, and then we'll do step 3 to try to fill in some pieces to make a slightly more accurate graph. So right now, what we have is a 0 here, a 0 here, and we have a 0 and our x-intercept in the middle. And we know our end behavior. My end behavior was saying that it was going up on the left side and down on the right side. And then I have all this other stuff in the middle. We will be connecting, and we know with multiplicity 1, we're going to pass through each of these and cross. So it's going to have that general shape. But just to give it a little bit more accuracy, let's check what happens at x equals negative 1 and x equals positive 1. Just to give our graph a little bit more accurate of a shape. So when x equals negative 1, my function gets me a negative 1 to the third plus 4 times negative 1. Well, this would be positive 1 minus 4, which is negative 3. And when x equals positive 1, I get negative positive 1 to the third plus 4 times positive 1. This is negative 1 plus 4, which is positive 3. So at negative 1, I'm down here at negative 3. At positive 1, I'm at positive 3. And this still isn't going to be 100% precise because we have all of those other points in there that we don't really know. But if I just connect this, crossing my x-axis at all of my zeros with multiplicity 1, and connecting it up, we get a general idea what the graph looks like. That's a pretty accurate representation right there. All right, let's do one more. Graph h of x equals 0.5 times x minus 1 times x plus 3 to the second power. So start with your end behavior. And remember, for the end behavior, we need to look at what the leading term is. Now this guy's completely factored for us, which is going to come in handy later. But we have to figure out what our leading term is. I know my leading term is going to involve the 0.5x. My highest exponent in here is just another x. And on this guy, if I distribute it all the way out, I would have an x squared as the highest exponent. So my leading term is 0.5x to the fourth power. So now I can look at what happens when x approaches positive infinity and negative infinity. As x approaches positive infinity, what happens to my function? Well, it's going to behave like that leading term. And when I plug in positive huge numbers, to the fourth power, it's still going to be a positive huge number, and it's multiplied by a positive. So it's going to positive infinity. Similarly, when I plug in a negative huge number, a negative to the fourth power makes it positive, and times another positive stays positive. So the end behavior is I'm going up because I got positive infinity, and it's going up on both sides. It goes up on the left and up on the right. All right, so that is the end behavior. Now let's find our y-intercept and our zeros with multiplicities. My y-intercept we get by plugging in 0 for my x. So I get 0.5 times 0 times a -1 times 9. All of that ends up being 0 because I'm multiplying by this 0 right here. So my y-intercept is the point 0, 0. Now what about the zeros of the function? The zeros of the function this is already factored for us, which makes it nice to see. This factor here gives me a 0 of x equals 0 with multiplicity 1 because it doesn't have any exponents on it. This factor gives me a 0 of x equals 1, also has multiplicity 1 because there's no exponent on those parentheses. And this factor gets me a 0 of x equals -3, but this one has multiplicity 2 because it has that second power on it. So I know the graph of the function is going to cross my x-axis at 0 and 1, and it's going to touch my x-axis at -3, but then it's going to turn around and go the other direction. Let's put everything we know on a graph so far, and maybe we'll plug in a few extra points to get a better shape. So everything that I know so far. I have a point at 0, 0. I have a point at 1, 0. That's one of my zeros. And I have another 0 over here at -3. And I know that the function is going up on both sides. And I don't know anything else that's going on other than when I get to -3, it's going to touch and turn around. And it's going to have to pass through on these other two guys. So we have the general shape in mind, but let's just plug in a few values to get a couple more points to be accurate. I will plug in -2, -1, and 1/2 just to get us a better idea. When x equals -2, my function is 0.5 times -2 times -2 minus 1 times -2 plus 3 squared, and I get 3. So I have a point at -2, +3. If I plug in x equals -1, I get 0.5 times -1 times -1 minus 1 times -1 plus 3 squared, and that gets me +4. So I have -1 and +4. And then let's just get one value over on this side. We'll do x equals 0.5. When x is 0.5, my function is 0.5 times 0.5 times 0.5 minus 1 times 0.5 plus 3 squared, and that is equal to negative 1.53125. So we'll just estimate that. 1/2 and about negative 1.5. So somewhere in here. And now we have enough that we can connect it and get sort of a decent shape to the graph. So I know I have to continue my curve, bounce here. I touch my x-axis and turn around. I'm going up. I have to connect. I have to reach my x-axis again, and I'm passing through it. Go to this other point we know, and I know I have to pass through the x-axis again, so I turn around, pass through, and connect up. And that's a very rough sketch of what it looks like. It's not perfect, but it gets you the general shape of what the polynomial looks like. All right, so that's all I have for you today. That was quite a bit of info about polynomials, determining end behavior, zeros, multiplicity, and learning about the intermediate value theorem. If you have any questions, feel free to ask them down below, or you may email me or come to office hours if you're one of my current students, and I'll see you for the next video.